I'm going to share the lessons that I learned from migrating HDF data to cloud. And the title of my talk is Our Earth Floating Cloud. Let me introduce myself first. I'm a software engineer at the HDF Group. And I enjoy playing golf. So I put HDF5 swag sticker on my driver. I'm also obsessed with HDF5. Whenever I play golf, I think about HDF. And I enjoy also learning earth science. If I see a golf ball, I think about that as HDF data and want to send it to the cloud. I'm so laser focused on this task. So let me first talk about our Earth. You know, universe was created like 13 million years ago. And compared to the universe, Earth is only 4 million years old. And for human, it's only 2 million. So human's presence is really short. I'm talking about universe because HDF can cover everything from Higgs boson to the black hole data. And Earth observation is much shorter history. It's only 6 years old. First satellite was launched in 1957 by Russia. And first weather observing satellite was 1960. In 1999, Terra was launched. And this is a very iconic event because it's the satellite that stores data in HDF. And this is the image captured by Terra Modis. And this is widely known by iPhone users because it was a default desktop background. And currently there are about 700 Earth observation satellites. And now I can talk about history of cloud computing a little bit. Internet started in 1969. And the web started like 30 years later in HTTP 1.0, RFC was written. In 2006, Amazon started web services with the two beta services, EC2 and S3. And in 2014, HTTP was modified to support range requests, which has a big impact for binary data streaming based on offset and length. And now we have a HTTP 2.0. Currently, big tech companies like Microsoft and Google join the cloud move, and they provide more than 100 products and services. So virtually anything can be run as a service in cloud, like AI, ML, big data. And even infrastructure can be defined by software. So together, Earth data in cloud has a really short history. 5 years ago, AWS started Earth on AWS project, and Google and Microsoft joined right away. And the approach is quite different. Google only provides APIs, although the underneath data is HDF. And Microsoft AI, they provide the raw data in blob storage as HDF as is. And NASA picked AWS. And GHRC, one of the NASA data centers, shifted their data service from on-prem to cloud. And at NCSA, there was a big project to collect all the Tera data into one collection. And we successfully put some sample data in AWS as open data service. So as of now, if you go to the search source data nasa.gov, there are about 820 collections on AWS. And almost half of them are stored in netCDF and HDF. So here's the latest example. Colab is another NASA Earthdata DAC, and they now publish data on AWS directly. So for example, there are like 1.9 million byte size netCDF HDF files. And good news is MATLAB can access this kind of data from S3 seamlessly. So if you read the data directly from S3, it takes like 0.5 seconds slower than accessing netCDF from locally. However, if you want to process the entire collection, the delay of 0.5 seconds magnifies to 80 minutes. And for storage cost, you can save a lot of money on S3 by sacrificing 80 minutes. And I mentioned about Terafusion because it's a really interesting data product. Each file size is about 15 to 40 gig. And there are 84,000 files in total, which is about 2.4 petabytes. And AWS could not hold all the data. And only 150 terabytes are available on AWS as a free data. And if you run MATLAB on this data, the delay becomes quite significant. So instead of 0.5 seconds for echo JPL product, the delay is 82 seconds. And if you want to process this entirely on AWS, the difference will become 80 days. So you may be wondering, what's the catch for those 80 days? And if you calculate the storage cost for 2.4 petabytes, it will cost like $200K for EFS system compared to the S3, which costs about $52K. And you cannot even hold this amount of data in EBS because there are 64 terabyte max. And here's another benchmark performance for reading metadata using MATLAB and GDAL. So if you use MATLAB, it takes about 3 minutes and 3 seconds for retrieving metadata only from a single Terafusion file. But if you choose a different software like a GDAL, and you run GDAL info program, it takes about half, 1 minute 41 seconds. So you need to choose software wisely. And some people argue that data format can make a big difference on S3. So this is another project that I was involved called the Power that can help energy company to locate the maximum radiance from the Earth to maximize their investment on solar panels and solar energy. And they use a jar because people say jar performs very well on S3. So we ran an experiment and jar is not that great. If I run the service, power service using Fargate and API gateway, S3 took about 36 seconds. And if you run ZAR on EFS file system, it takes about 0.8 seconds. So although data format, yeah, people may think it matters a lot, you cannot overcome the performance of a cheap service, and you get what you really pay for. So don't be fooled by the performance improvement through DAS clusters, which often goes with JAR, and it costs extra money for computing by running the clusters. And there are some really good format indeed. And one of them is Arcgis CRF, Cloud REST format. And when we run that experiment for another NASA project, it worked. Performance was really good. It has only 0.2 second difference for some service like exporting imaging from the data. But this is a proprietary format, so only Arcgis library can handle it. But there's also another catch. They rewrite data by indexing along the time dimension. That's why they perform well. So original data, for example, 178 megabyte netCDF4 becomes 2 gigabyte CRF on S3 when no compression is used. Even if you use compression, it's still twice bigger. And there is another limit, which is you cannot have more than 65,000 time slices. So this format is not appropriate for Terafusion. They can span over 20 years. And transformation time, you cannot ignore that. It takes about 2 days to convert 1 year netCDF to CRF. So it will cost extra money to process the transformation. And the beauty of cloud definitely has you can easily scale vertically. So like several years ago, we ran an experiment running Hyrex on top of the series HDF4 data on S3. And again, if you choose the more powerful machine, definitely you can improve the time, but you need to pay more. T1 Micro is a free service, but it will take about 50 minutes per request. But if you choose a larger instance, it will be much faster with the extra cost. And this is from 2017 test. And horizontal scaling also can help to improve performance. So the more you run the cluster, it will get faster up to a certain point. And if you compare, the parallel computing framework also matters. So Dask is much better than PySpark. And we use the technique by storing metadata in Elasticsearch. And this is something you want to try if nothing works. So 4 days ago, I read a very interesting article from Korean newspaper. And they purchased 3 supercomputers for climate forecasting and paid like $80 million. And when they sold those 3 supercomputers, they could collect only $66K. So many taxpayers in Korea complained that why they spend so much money, yet they cannot get accurate forecast. But in my opinion, that's not bad because they reclaimed the 66K out of 180 million. Because if you run this on cloud computer, you get absolutely nothing after you're running the cloud service. But there's some chance that you may get some profit by running on cloud instead of supercomputer because there's a little maintenance overhead and you can increase storage and computing on demand. So here's my hypothetical game called this for climate forecasting squid game. The prize money is 185 million, which is what Korean government spent for 20 years. And your job is to build an AI or ML machine learning system that can predict weather actually. And the rule is winner takes all the money, like a squid game. And whoever finished first with a 99% accuracy wins. And your profit is minimizing cloud cost, so you can maximize the profit. So time is important. So to win this, there's some dilemma. If you want to make the maximum profit, time may take longer, so you may lose the game. But if you want to maximize the performance, you may lose dollar with no profit. So should you participate in this game? And here are several winning strategies. One of them is you need to calculate everything in advance. And every cloud vendor provides a cloud estimator, so you have to use it. And when you do that, you need to know the limits of each service. For example, if you want to run AWS Lambda over EC2, you may be happy there because it's simple and you pay as a function as a service. But you should know the limit that it can run only 15 minutes. So we tried that for NASA project, and GDAL worked beautifully because they could serve data within 15-minute bound, but threads could not work. And the similar issue was, timeout issue was reported by PODEC recently. Another winning strategy is using the existing solution. Cloud vendors provide 200 for AWS different services. So whatever exists, you better buy it instead of developing your own. So for example, if they provide the forecasting model, trend model, just use it. And if they don't provide, you better read their best practice architecture in use cases because they are proven to work. And here's my experience. I want to transfer big Terafusion files and ZAR between EFS and S3. And they provide a service called data sync, which costs more, but it was much faster and reliable. I tried to save a lot of money by using free tier EC2 instance and S3FS, which is open and free. But they always fail at the end of the transfer, which caused a lot of frustration. And another strategy is avoid the transformation as much as possible. So if you look at SageMaker, they relies on Apache Drill for in-memory processing for learning and training. And Apache Arrow can definitely read the table from pandas. And pandas can create data frame from XArray, which can read the netCDF and HDF5 on S3 through H5 netCDF module. So people think that, oh, that's great. I can use SageMaker to process Terafusion on S3, but that's completely wrong. If you look at this Colab, Google Colab output, there's no errors between transformation, but if you look at the bottom of the screen, the data variables is 0. So although they see dimensions, variable, and coordinates, there's actually no data underneath. So if you run this on cloud, you get really nothing, just wasting your money and time. The last winning strategy is lead us not into cloud and deliver us from bugs. For example, Apache Drill can handle Terafusion file locally. And I was very curious why why you cannot. So you need to ship this kind of software to the cloud, hoping that it will run in the cloud. It will never happen. So you need to purify all the software from the bugs. And even if you fix only one small bug, the saving is tremendous at internet scale in cloud. So for this example, it turns out that Java memory configuration was wrong. So if I fix that configuration, you could run it successfully, although it's very slow. It's like 1,630 seconds, and which is about 30 minutes. And if you remember, MATLAB took about 3 minutes, and GDAL took 1 minute, 50 seconds. And that's the end of my talk. And this work summarized a lot of grants from NASA. So I'd like to thank all the collaborators and funding agencies for this work. So if you have any questions and comments, yeah, this is the time. And please ask the right question. Like, for example, if you want to improve like 1% of machine learning algorithm accuracy, you may need 100,000 of more examples necessary. So you need to ask whether it's worth pursuing that question. So if I'm the Squid Game participant, I'd rather give up right away because 99% accuracy is not worth pursuing at all.
Thank you, Joe. Are there any questions or discussion? Thank you, Joe. Your talk is always enjoyable and controversial, so I hope it will spark a little bit discussion here.
There is one question in the chat window. Laurie, is it something that anybody can talk by opening their microphone?
Yeah, everyone, yes. Go ahead and unmute if you'd like. I'll read Ed's question here in chat just in case he doesn't have a mic handy. He said, thanks for the interesting talk. Have you tried using the new NC-ZAR compatibility recently released in netCDF?
Yes, we tried it and we failed miserably with the power ZAR format. So we submitted the bug ticket to the netCDF mailing list. Looks like NC-ZAR has additional metadata that tells that this is NC-ZAR. So the power ZAR was created by Python, and there was a little bit compatibility issue. And NC-ZAR is a big buzzword. People are really waiting to use it. And MATLAB people are asking, those NASA people are also curious about NC-ZAR, and they want to access using the C library for performance. Hopefully, NC-ZAR performs well as like GDAL.
And of course, it was one person's experience, so maybe different people will have
definitely
experience. So And many of those technologies and experiments are new. They need refinement and more deep studies. So it just draws, as he said, it was his experience working with different data sets using cloud. But it's very interesting, and really appreciate your insight, Joe. Thank you.